Dragon is in countdown. Falcon 9 is in startup. Dragon, SpaceX, go for launch.
Hello and welcome to NASA's Kennedy Space Center. I'm Tyler Green with NASA Communications. Today we are counting down to the launch of SpaceX's 25th commercial resupply mission to the International Space Station for NASA. On board is more than 5,800 pounds of science experiments, crew supplies, and other cargo. But today we'll be focusing on those missions and experiments that are especially focused on Earth science. We'll also discuss NASA's climate research portfolio and how we're working to better understand climate change. I won't need to talk about that too much, though, because we have a great panel of folks here today who will do just that. So let me go ahead and introduce them. First up, we have Kate Calvin, NASA's Chief Scientist and Senior Climate Advisor. Heidi Parris, Associate Scientist of the International Space Station Program. Mike Roberts, International Space Station National Lab Chief Scientist. Rob Green, Senior Research Scientist at the Jet Propulsion Laboratory and the Principal Investigator of the Earth Surface Mineral Dust Source Investigation, also known as Emit, a NASA instrument which will identify the composition of mineral dust to see what effects it has on the planet. And finally, Paula Pereira, Mechanical Engineering Integration and Testing Lead of BeaverCube, a CubeSat out of the Massachusetts Institute of Technology. We'll first hear some brief remarks from everyone, and then we'll open it up to Q&A for media who are here in the room, as well as on the phone line. We'll also be taking questions via social media. You can submit a question now for us to ask later by using the hashtag AskNASA. And with that, I will turn it over to Kate Calvin to kick us off.
Thanks, Tyler. So one of NASA's most important missions is our home planet. We are the U.S. space agency that does end-to-end research about Earth, including observations, models, and technologies. You load the first animation. We have more than 24 satellites and instruments in orbit, including several on the International Space Station, that let us know what's happening on Earth here today. This animation is showing our current Earth-observing fleet. From this fleet, we can see things like carbon dioxide, clouds and precipitation, vegetation, changes in the mass of ice sheets, and much more. Since we've been observing the Earth for decades, we can see not just the state today, but also how it's changed over time. We have more satellites coming up in coming years, including one later this fall called SWAT that'll look at water. And we're also starting the formulation of the Earth System Observatory, the next set of Earth-observing satellites that will work together to provide a 3D holistic picture of the Earth. In addition to observing the Earth, we also develop technologies that can help us mitigate or adapt to climate change, like our sustainable aviation technologies. We've worked with the aviation industry for decades to reduce energy use and emissions in aircraft. If you show the next image. We're also developing new technologies. So later this year, we'll be testing the X-57 shown here, which is an all-electric aircraft. So we'll use this to test the airworthiness of battery and electric technologies. We also live and work in space on the International Space Station. Mounted on the space station are several Earth-observing instruments. There's several on there today, and there's more going up tomorrow. So we're here to talk a little bit about Emit, one of the instruments that will be put on the International Space Station. So if you load the last animation, this is an animation of the International Space Station designed to show Emit. So Emit is an instrument that will look at mineral dust, and it is on this particular resupply mission, and you'll hear more about it from others on the panel today. So thank you, and back to you, Tyler.
And now we'll go to Heidi Parris, Associate Scientist of the International Space Station Program.
All right, thank you, Tyler. Well, the International Space Station is a state-of-the-art orbiting laboratory, and it's enabling scientists from around the world to take advantage of a very unique research environment. That research environment includes sustained access to the microgravity environment. It includes exposure to the extreme and harsh conditions of space. And it also includes access to a platform in an ideal location in low Earth orbit that lets us study how the Earth is changing over time. So the research on board the space station spans every major discipline, including biology and human research, physical sciences, earth and space sciences, educational outreach, and also development and demonstration of new technologies. But all of that research is being done with a single goal in mind, and that's to bring benefits to us as a human race. And sometimes those benefits look like new medicines, new technologies, or improved products that we see impacting our daily lives. And sometimes those benefits look like the discoveries that can inform and impact society on a more global scale. So when it comes to climate research specifically, there are a couple of factors that make the International Space Station a really great place to study the Earth. The first one is the fact that we have a crew on board. And if you can cue up that first picture. So astronauts have taken over 2.5 million photos of the Earth during the time that the International Space Station has been on orbit. And that's part of one of the longest running investigations that we have on the ISS called Crew Earth Observations. And those photos are used by researchers on the ground in a variety of ways, from tracking the changes in volcano and glacier movements to tracking how the migratory paths of endangered species of birds have changed over time. And those photos are also used to aid in response to disaster situations, things like wildfires and hurricanes. The second reason that makes the ISS such a great place to do Earth science is the fact that it has a very unique orbit. So it passes over 90% of the populated regions on the Earth, and it does it at all different times, day and night. And that allows researchers to collect a very comprehensive data set that most remote sensing satellites don't necessarily see. If you can put the second image up, please. So the International Space Station has a suite of externally mounted remote sensing satellites outside of the space station. These are studying the Earth and the way the ecosystem is changing in a variety of different ways, and you'll hear more about some of those that are coming up in just a few minutes. But one thing that I find very interesting is that although each of these experiments was designed independently, the nature of their observations is very complementary. So it really gives us an unprecedented opportunity to understand the interdependency between all of the changes that we're seeing occurring within our ecosystem. With that, I'll turn it back to you, Tyler.
Great. Now we'll go to Mike Roberts, International Space Station National Lab Chief Scientist.
Thank you, Tyler. In addition to the wonderful instruments and ability to support research and technology development that addresses so many of the needs of human society, not just here in the United States, but around the world, the International Space Station is also unique in its ability to host the International Space Station National Laboratory. The ISS National Laboratory, unlike a lot of the other projects on the International Space Station, not only seeks to address goals that benefit humanity and are defined within NASA's research portfolio, the ISS National Lab enables access by other government agencies within the United States. Corporations and academic institutions directly gain access to space to support those same important goals. So with the subject of climate change and our understanding of the need to not only think globally but act locally in addressing that, the ISS National Lab portfolio has for a long time included several projects, so many of them funded directly by industry and other government agencies, focused not only on climate change but issues of sustainability. We could have the first graphic, please. This is a photograph from on board the International Space Station taken just last year with Shane Kimbrough. In this photograph, Shane Kimbrough, the astronaut, is interacting with an experiment that was sponsored as part of a sustainability challenge that was funded by the Target Corporation. So Shane is working with a cultivar of cotton. Cotton is extremely important to the textile industry. It's a worldwide agricultural commodity that's grown in many different regions across the world. And in all of those regions, it shares a common deficit in that it's a very prodigious consumer of water. So in many of these areas of the world where cotton is grown, it's an important agricultural commodity, but it also is competing for water resources. So Target Corporation contributed $1 million in partnership with the ISS National Lab to sponsor 3 research efforts utilizing microgravity and the unique aspects of exposure to that environment to support investigations in that area. If we could have the next photograph. These investigations continued earlier this year. This is astronaut Mark Van de Hey in January of this year interacting with a second experiment, again, focused on cotton calluses in the microgravity environment. So when I mentioned think globally and act locally, these are not Earth-observing sensors, but these are real-world solutions that are being tested in a harsh environment in microgravity that challenges plants in order to understand how to address the effects of climate change and improve our ability to sustain our operations going forward. On this mission to space that SpaceX CRS-25 is going to execute, we'll have the next chart, please. We have another example of commercial engagement supporting research and technology development on the International Space Station. In this example, Procter & Gamble is going to be flying some commercial products that they offer here on Earth for cleaning textiles. The advantage of utilizing these textile cleaning products in the spaceflight environment is to understand how we can use them because they don't require access to water. So Procter & Gamble has flown a series of experiments focused on improving the quality of their consumer products, and some of these are now beginning to look at ways to address water scarcity, which is an issue for many consumer products. In addition to these efforts, the International Space Station National Laboratory has also sponsored and partnered with other industry organizations, including Estee Lauder, at our ISS Research and Development Conference in just over a week in Washington, D.C. We'll be announcing 2 winners of the Estee Lauder Sustainability Challenge in partnership with the ISS National Lab that will sponsor 2 additional flight experiments leveraging the unique environment of the International Space Station to support research that can directly address some of the effects of climate change and sustainability issues confronting us. So the International Space Station National Lab supports NASA and looks forward to this mission tomorrow and hopes to be able to expand the portfolio for climate change science in the future. Back to you, Tyler. Thank you.
Thank you, Mike. And next we'll hear from Rob Green, Senior Research Scientist at the Jet Propulsion Laboratory and the Principal Investigator for Emit.
Thank you. I'm excited to talk with you about Emit today. Interestingly, the Earth has a mineral dust cycle, and minerals are the particles that make up rocks. And in the arid land regions of the planet, under conditions of high winds, these minerals get launched into the atmosphere where they can heat or cool the planet, they can form clouds, and there's a host of other interactions they have with our system. We're going to close a gap in knowledge about those mineral dust source regions of our planet. Right now, our knowledge is traced to about 5,000 mineral analyses where minerals have been collected and analyzed. When Emit completes its mission, we will have 1 billion direct observations of the mineral composition of the Earth's arid land. So that's the gap that we're going to close with Emit. Could I have the first image, please? So this is a depiction of Emit. We're very pleased to be going to the ISS. It's the perfect orbit for us. The ISS covers the arid land regions of our planet from Africa to North America to Australia to South America just wonderfully. And again, this image depicts how we'll peel back that current yellow understanding of the mineral composition and really put high fidelity knowledge about the minerals that are on the surface of the Earth that can get launched into the atmosphere and interact throughout the Earth system. Could I have the next slide, please? Again, to depict this is depicting the impact of mineral dust throughout the Earth system. It's an important cycle. When those dust particles get lofted into the atmosphere, of course, initially, if they're dark or bright, they can absorb or scatter energy, heat or cool the Earth. They play a role in cloud formation. When they're deposited in oceans, they fertilize those oceans, causing phytoplankton blooms. When they're deposited in terrestrial ecosystems, they can be important nutrient as well. When they land on snow, where I come from in California, they greatly accelerate snow melt, and that impacts water resource availability both in California and in many parts of the world. And then directly, when they interact with us on the surface, they can be a visibility hazard and also a toxic hazard in terms of their particulate nature. So that's the element, and we're going to address that by understanding the composition of those dust particles in their source regions with these measurements. Next, I think I have a depiction in the next video of what it looks like when mineral dust is launched into the atmosphere. This is from one of my co-investigators, Carlos Perez in Morocco. He was making ground measurements where they were actually captured in a dust storm on the surface. You can see what it's like when those conditions of high winds loft the dust into the atmosphere. And then if we go on to the next slide, I want to drive home the point that this is a global phenomenon, that these dust storms can be enormous. This is one from 2020, where you can see the dust leaving North Africa, and it actually traveled all the way to Texas, over Florida. It changed the visibility. There were hazard implications. It fulfilled all those roles. So this is an important cycle in the Earth system. It fits in with NASA's capability, especially with this new Earth System Observatory, to bring higher fidelity knowledge about these sub-elements of our Earth system. So I can go to that next image, please. And the approach we're going to take to measure the surface composition, I'll just highlight briefly here, is we're going to use imaging spectroscopy. We're going to look at the light that has interacted with the minerals on the surface of the Earth, and that light has been absorbed preferentially based on the molecules, the minerals, and that fingerprint that we measure with Emit from the ISS is the way we'll be able to determine what the mineral composition for the arid land regions of our planet. And we'll also hopefully be preparatory again for NASA's upcoming Earth System Observatory. Our measurements will be complementary, and we'll learn things that will be relevant for that exciting future that's coming with NASA. Thank you. Pass it back to you, Tyler.
Thank you. And now over to Paula Pereira, Mechanical Engineering, Integration, and Testing Lead of BeaverCube out of MIT.
Awesome. Thank you, Tyler. So spacecraft come in many different sizes and shapes. The ISS, for example, is huge, but BeaverCube is right here. It's very small. This is a copy, an engineering model, real size, of BeaverCube. It's a 3-unit CubeSat, which is about 4 inches wide, 4 inches deep, and 13 inches tall, and it weighs less than 8 pounds. BeaverCube has 2 main mission goals. The first one is to help better understand the fronts of ocean, and the other one is to demonstrate the use of an electrospray propulsion on board the CubeSat. So to be able to understand these ocean fronts, BeaverCube has 3 cameras, 2 on the infrared spectrum and 1 on the visual spectrum. The 2 infrared spectrum cameras are going to be taking pictures of the top of the clouds and the surface of the ocean. And with that, we can track the temperature of the cloud tops and the ocean surface. And also the other camera, the visual spectrum camera, is going to take pictures, colored pictures of the ocean, so we can track phytoplankton, which is a very important factor in producing atmospheric oxygen. And we are the Massachusetts Institute of Technology, so Massachusetts is a very important state for us, and there is a lot of effects on climate change on the water of Massachusetts. It's getting very much warmer, and it's deeply affecting the water concentration of animals and sea life in there. So we are going to focus on taking pictures and tracking the temperature and climate change of that region. The other goal of BeaverCube is to demonstrate the use of an electrospray propulsion. We are partnering with Axion Systems. They have developed this novel electrospray propulsion unit, and we are putting it inside our spacecraft with the goal of giving a small boost in our orbit so we can go a few tens of meters up in our orbit and extend our lifetime a little bit, and so it takes longer for us to deorbit. BeaverCube was developed at MIT by graduate and undergraduate students under the guidance of Professor Carrie Cahoy, the project principal investigator. If you bring the first image, this is a computer image of BeaverCube, and you can see that there are many instruments and many electrical boards inside it. 3 of those boards were developed by students, and the external structure was also developed by students. The next image. shows the outside complete version of BeaverCube. BeaverCube was completely assembled, integrated, and tested inside clean rooms at MIT, also by students. And the last image shows BeaverCube being integrated inside the NanoRex deployer, which is the thing that is going to be handled to the astronauts inside the International Space Station so they can deploy BeaverCube from the ISS into its orbit. And we have the hope that with such a small and simple spacecraft, we can pave a way to have more CubeSats and more spacecraft that are small and simple, tracking the temperature and the climate change around the entire globe so we could better understand and tackle this issue in the future. Back to you, Tyler.
Thank you, Paula, and everyone for those overviews. Now we will go into our Q&A portion. I'll first open it up to folks that we have in the room if there are any questions. Yes, thank you. Could you please just state your name and your affiliation, and we'll get to you.
Hi, Emily Speck with Fox Weather. My question's for Paula. Can you talk a little bit more about the propulsion system? How does that work compared to your average propulsion system?
Okay, so there are two big kinds of propulsion system. One of them is chemical and the other one is electrical. So this one is electric. So it has small ions that are shoot because of a different voltage levels, and that difference in voltage shoots tiny liquid droplets outside, and that those droplets going out on the back of the system pull the spacecraft forward. This unit was developed by Axion Systems, and they have many interesting documents and papers online that you can search for. And we are going to test it inside a CubeSat, which is very rare to have a propulsion unit inside a CubeSat because of the size that it has to be. So we hope it works very nicely and increases our orbit altitude.
Hi, I'm Jim Siegel. I'm with NASA Tech. I'm not sure who to direct this comment to, but you've all described a variety of climate-related issues, and so I'm interested in two things. First of all, who decides, or how does NASA prioritize all of these issues and decide who's going to get what kind of time on the International Space Station? And then secondly, is there someone that puts all of this together to provide kind of a comprehensive look at climate change and on the Earth from NASA's point of view? Thank you.
Heidi, do you want to start?
Yep, I can start with that. From our prioritization and planning process, we have a number of different science sponsors that are responsible for all of the science that is going on board the station. They take ownership of that science. So I can't speak to the process of how each individual organization decides which science they're going to pursue, but once that science is decided or selected by those funding and sponsoring organizations, it comes to the international program, International Space Station program, and at that point we compile all of the requested science along with the priorities, and it goes through multiple planning forums within the ISS program to make sure that we have agreement and input from all of the sponsors that have science that wants to be looking at Earth science or at any of our different areas of science. And then once those priorities are agreed upon, that goes to an existing external site working group, and they start looking at assigning those payloads to specific locations with specific launch service providers, and then putting those launch service providers on contract for those experiments. And I will note that this planning process has to start very far in advance. It's critical to make sure that we are maximizing the use of the International Space Station for scientific research, and in order to do that, we have to plan early because these experiments take a long time to get integrated and designed.
Kate, do you want to add anything just about complementary?
Yeah, just touch on the second part of your question. So NASA does have climate research throughout the agency. Many of the different teams, the aeronautics, space technology, space operations, and the science mission directorate. And I am serving in a dual role of chief scientist and senior climate advisor. And the senior climate advisor position was created to help connect all of the climate research that's going on throughout the agency and to communicate that externally and to people like you or to other agencies and international partners.
Thank you. Do we have any other questions in the room? Yes.
Jim Siegel again. I've got a lot of questions. So the International Space Station is going to go out of existence soon. Well, not greatly soon, but in a few years. So what's going to happen to all the needs that you've just described? Are there going to be other space stations, or how are all of these, all the work that you're doing, how is that going to continue once the space station goes out of existence? Anybody?
Want to take that or want me to?
I can certainly speak to the science that I'm involved with. I'm very fortunate that there is a plan in the Earth System Observatory. One of the instruments will be part of that into the future, called for in the decadal survey for the Earth Science, NASA, is SBG, Surface Biology and Geology. And it includes an instrument that's quite similar to the instrument in Emit. So I expect that will be a wonderful opportunity. In fact, expand the class of measurements of the type that we're talking about here with Emit. For a broad set of objectives, but they will also help me carry forward the mineral dust investigation, looking for changes in sources through time. So I think that turns out to be very fortunate with me, though I will be very sad at any day that the ISS doesn't continue to exist. It's a spectacular platform from my perspective.
And I can speak to that a bit more on a holistic level in terms of ISS research. So there is a significant amount of outstanding research going on board the station. And in fact, now we're just entering into the third decade of the existence of the International Space Station. And the ramp up that we've seen in being able to utilize the ISS for research has been exponential every year. We've now had over 3,000 different investigations through the lifetime of the space station, and a lot of those investigations are building upon each other. And so we certainly don't want to get into a situation where we don't have a space station to continue this research. So that is one of the key new facilities that's being developed, that's being discussed, is how do we transition from a space station where it's government run by NASA and the other governments that are involved in the international partnership, to a space station that is run by private industry, by commercial companies. So we have a number of we call them commercial LEO destinations, where we're looking at making sure that before the ISS mission is complete, we have another commercial space station that can pick up that research and continue on doing that research in the future.
Okay, so that's kind of thing that's ongoing or has started already. Is that correct?
I can pick up just a little bit of that. So the commercial LEO destinations, one of the first one that's been funded is Axiom. So Axiom Space is going to be part of the International Space Station within a couple of years. And then there are 3 additional ones who are developing free flyer platforms. So NASA has an ISS transition plan that Heidi spoke to that defines what the plan is, and it's updated annually. So as these commercial approaches to establishing new R&D capabilities in space become reality, they'll be able to be more responsive. So in the same way that we've seen significant improvements in launch technology for cargo and crew launch to the International Space Station, NASA realizes the value of having commercial engagement there too. So the commercial LEO destination program is designed to kickstart that program going forward so that there will not be a gap in R&D capabilities.
We will go to an online question that we have. This is probably best addressed by Rob, of course, and then Kate, you may have something to add. Why is Emit studying mineral dust?
Emit is studying mineral dust because it's currently an unknown element. We don't really understand, based on the IPC, whether mineral dust heats or cools our planet right now. The sign, not just the magnitude of how much it heats or cools, but whether it heats or cooled, is still uncertain. So we identified that gap when we wrote the Emit proposal, that's something we could address, and we had a strategy to address it by, again, moving from a situation where the source regions are identified by 5,000 mineral analyses to now 1 billion direct observation of what minerals are on the surface, and then using that new information from Emit in advanced Earth system models, again, to model how mineral dust heats and cools our planet. And it will also allow us to address those other elements and impacts to the ISS. So we wanted to study it because there's a gap in our knowledge. It relates to climate now and in the future. And that will allow us to have better information to adapt to climate change and perhaps even make some decisions to mitigate how much mineral dust is available to be emitted into the atmosphere and impact the Earth system.
Yeah, I just would agree with Rob. I think mineral dust, we know, we understand some of the processes. The darker colors absorb sunlight, the lighter colors reflect it, but we don't have comprehensive measurements. And so we still have an uncertainty of what the total net effect is of mineral dust. And I think Emit's really going to help us understand that and improve the models, as he mentioned.
Thank you. Another online question. This is for you, Rob. When can we expect to get data back from Emit? What is the timeline?
Okay, we're very excited to be manifested for launch tomorrow. It will take about 2 weeks before we're installed and begin to cool down. So we expect to we'll see our first spectra at the end of July. We're committed to get those data out to be available as quickly as possible. I think our requirement is within 2 months. We'll try to do much better than that. All the Emit measurements will be available for the public and other scientists from the NASA Land Processes DAC. So we're going to have all the data. They'll be accessible and downloadable. Starting in about 2 months after the end of July is when you'll get the first cut of Emit data that will be totally available, and all the data consistent with NASA's Earth Science Data Policy and open science will be available throughout the mission, and at the end of the mission, of course, it will all be. And I'll just chime in on the open science. We've already put the Emit algorithms, as you can imagine, going from what we get to measure, photons at the top of the atmosphere, to surface mineralogy. Those are sophisticated algorithms. They're already available on GitHub, on the public GitHub. We're trying to lean forward to this concept of open science so people can see exactly what we're doing and help us improve.
Thank you, Rob. And our next question comes from social media for Paula. Where did BeaverCube get its name?
That's a great question. So the mascot of MIT is a beaver. Beaver is known as the engineer in the nature, so that's where the beaver part comes. And the fact that it's a CubeSat, there comes the cube. So it's a beaver and a CubeSat, BeaverCube.
Thank you. And this next question is for Heidi. How has the International Space Station benefited climate research so far?
Yeah, so that's a great question. We, as I mentioned before, we have a number of different Earth science investigations, and they all are collecting something different, but the nature of their observations means that they can tell us a lot about how the Earth is changing overall. I can give it just one example maybe of one of those investigations. It's called EcoStress. It's primarily looking at how the thermal changes on the Earth's surface and also how plants respond to water stresses. The data for this investigation has already been used in a number of ways, from looking at how to reduce heat that's absorbed into city surfaces, to looking at better water allocation, reducing fire danger, helping farmers understand how to most effectively and efficiently water their crops. And one specific example with EcoStress that I find really interesting, it's been helping with an initiative to reduce heat in urban areas. So it's part of a pilot program called Cool Neighborhood, and they're basically looking to apply a thermal resistant paint to surface structures in areas that are particularly susceptible to excessive heat, extreme heat. The EcoStress data and instrument has been invaluable in helping those researchers understand which areas to target, and also in evaluating how effective this treatment is to these surfaces.
Thank you. This next question comes from social media for Mike. Kate, you may have something to add here as well. Are there future areas of opportunity that you think would be worth researchers exploring that could enhance our knowledge of our planet and or climate change?
Yes, an unmitigated yes. There are opportunities, obviously, through NASA Earth Science to advance sensor technology development and use the data sets that Rob mentioned that are publicly available to improve our understanding of the pace of climate change and localize the effects of that climate change going forward. From the perspective of the ISS National Lab, we've seen significant engagement from the commercial sector as well as other government agencies. We have active joint solicitations with the National Science Foundation every year that focus on fundamental physics, and the connection between the fundamental physics experiments that are sponsored by National Science Foundation and climate change are rather profound in that some of these investigations are looking at the effect of liquefaction in soil systems. So one of the things that we're seeing with changes in climate patterns are increased patterns of mudslides and debris slides, and we don't fully understand how that happens, the pace at which it happens, and how to combat it. So fundamental science feeds into those applications with real-world effects for climate change going forward. So there are many opportunities through engagement, again, with NASA and ISS National Lab, in addition to sensor development. Rob mentioned in the transition from International Space Station, there will be new platforms available to offer Earth sensing and space sensing capability. So there are many programs right now that are looking at ways to improve the quality of data from those sensors. Almost nothing happens now unless it's multispectral. So there's also, as Rob mentioned, a lot of interest in understanding data fusion, how to combine data from multiple sensors or single sensors so that they can be most usable to inform the research community.
Yeah, and just to add to that, so one of the processes that the National Academies leads for NASA is to identify the most pressing questions in different science areas. This is called the Decadal Survey process, and the Earth Science Decadal Survey came out a few years ago, and it identified some of the most important questions related to Earth. And we are using that Decadal Survey to design the Earth System Observatory. So we tailor our upcoming missions and observations towards the questions that are relevant there. And so there's a lot more we can learn about the Earth, and that process helps us identify that. I'd also just say, working at NASA's, really brilliant engineers and scientists and people developing technologies, and they always find innovative ways to take what we develop for one area and apply it somewhere else. So some of the technology in the International Space Station for the life support system has Earth applications. We also use some things from the sensors developed for one purpose, and we find innovative ways to observe something different. And Rob mentioned some of this, some of what's in Emit will go into other later missions, and we're continually doing that and learning more about our Earth and also identifying new ways to observe it and interact with it.
Thank you, Kate. Before we open it back up to questions in the room, I would just like to remind folks on the phone line, you can get into the queue to ask a question by pressing *1. So with that, we'll open it back up to the room if we have any questions.
Hi, Emily Speck with Fox Weather. I wanted to follow up on the tide experiment. So is the idea that you could do laundry without water? Is this something that you want to apply to Earth? Someone here wouldn't have to go to a laundromat? Like, what's the real world kind of application there?
Yeah, so the real world application first and foremost is for identifying a way to clean textiles in the space environment where water is a very precious commodity, right? A gallon of water is a little over 8 pounds to launch into space. So NASA has invested significant resources into understanding how to recover water. So they have environmental control and life support technologies that have been developed for use in spacecraft that have already translated back to Earth. This is what I would characterize as kind of the next step in that, and it's being led in part by commercial companies such as Procter & Gamble, who are always seeking to improve not only the performance of their consumer products, but also lessen the footprint that they have on our environment. So there's always an interest in maintaining the ability to clean without utilizing lots of water in that environment. So the initial tests are primarily going to address space applications. But if Procter & Gamble is fortunate in and they've achieved this before, they've flown several investigations focused on colloid chemistry in the microgravity environment, and that led to direct improvements and the generation of intellectual property that were incorporated into their products. And it's my belief they're looking to see the same thing here with this simple test going forward.
You can go to our next question in the room.
Jim Siegel again. Kate, I believe that you showed a picture of an electric plane. So electric car sales are starting to take off. Oh, no pun intended. Here in the United States and around the world. So what would be your outlook of airplanes being powered by electric propulsion?
That's a great question. So we're doing a lot of research into this now. So the X-57, which is the image that I showed, is an all-electric plane that we're testing. It is a small aircraft. We also have other flight research into hybrid electric aircraft, which are that we're testing out. And I think we're in more of a research organization, so we do research into the aviation technology, and then we turn that information over to industry to use going forward.
Are we talking about 10 years, 20 years for this to become common, or what do you think?
I don't have a clear answer on that. I think right now we're focusing on the research and getting it out there, and we'll test the X-57 now. But there's also infrastructure involved in a transition like that, and I'd have to get back to you on or put you in touch with an expert on that.
Does there look like there's a lot of interest on the part of the airline manufacturers like Boeing and so on to get into this, or are they resisting, or what's that look like?
I can't speak to that. I can only speak to what we're doing here at NASA.
Okay, thank you.
Okay, we will take some questions that we have now on the phone line. First up is Rachel Rodriguez with Inside Climate News. So Rachel, over to you.
Hello, thank you so much. This was an amazing conference, by the way. My question is about the BeaverCube. I know it was mentioned that images will be taken from the BeaverCube, and I was just wondering what, or if there are distinct differences between the images that will be taken by the BeaverCube versus what is already taken on the ISS. I know it was mentioned the BeaverCube might focus more around Massachusetts, but just thought I'd ask for clarity's sake what the main differences are in the images that will be taken. Thank you.
Sure. Thank you for the question. So the imagers that we have on BeaverCube are different sizes and different quality, I would say. If you look at the amount of pixels that you have per kilometer, it's a small satellite. So probably what we have here has a lot less resolution than what is available in the International Space Station. The big goal of having such a small satellite like this is that we can have multiple of it. So the International Space Station is very big and expensive, whereas a satellite like this is relatively inexpensive, so it also is relatively quick to develop. So we can have multiple versions of a small satellite like BeaverCube flying over different locations. So we could have constellations, and we could have tens or even hundreds of small satellites like this taking pictures that are infrared and visual spectrum images of different locations around the globe. And when we have all those satellites doing that, we could have a very higher frequency of pictures being taken, and that would increase a lot the time or resolution of images, and we would help us track ocean masses and help track the changes in climate and water.
Thank you. Our next question on the phone is from Philip from Popular Science. So Philip, over to you.
Hey, thanks so much. This is a question about Emit. You mentioned there being around 5,000 existing mineral analyses and sort of trying to close this knowledge gap with the billion observations the Emit project is going to produce. And it sounds like those existing analyses give you a really different data resolution from the remote observation. So I was just hoping you could talk through the distinction between sort of what you're able to learn with this remote sensing data versus whatever these 5,000 existing analyses look like.
Sure, I'll do my best to answer that. So the existing situation is there have been these 5,000 locations on Earth where mineral samples have been collected and analyzed in detail about what different minerals are there and what the proportions are. And then they've used existing very coarse soil maps to say, okay, if those minerals are in this soil map, then they're in that same soil on another continent. And that's considered to be a huge uncertainty, and there's evidence that that is the reason that the climate models aren't being validated. The Earth system models aren't validating as well with existing measurements. So that's the gap we're proposing. Now, we're using a different technology. We're not going to be touching the minerals and doing chemical analyses. We're using spectroscopy, but fortunate, we get to see the minerals on the surface in the arid land regions and how light has interacted with them, and whether it's an iron oxide, kind of like rust, or a carbonate, or a clay, those different mineral molecules leave fingerprints on the light we get to measure. So we can look at those fingerprints, which we'll see in the imaging spectrometer, and accurately assign the mineral compositions over the arid land region of the Earth. So we're going to bring that fidelity. Now, we've tested this and in fact compared it to the existing maps and showed that we deliver a much more accurate result about what minerals are present directly on the surface that are there to be emitted into the atmosphere. So I hope that answers your question. Otherwise, I could follow up if I haven't hit it quite right.
That was perfect. Thank you.
Thank you. And we have one last question. This might be best for Kate or really anyone who may want to chime in for other projects. What other missions or projects are on deck for NASA this year in regards to climate?
Yeah, thank you. That's a great question. So that we have a satellite mission launching in November called SWOT, the Surface Water and Ocean Topography Mission. And this is a mission that's going to help us better understand both freshwater and salty water bodies. So for freshwater, it'll give us the first global survey of water running through rivers and lakes. This is very similar in terms of the sparsity of observations to what Rob has described for Emit. So right now we have information about water running through rivers and lakes through gauges, and we don't have a comprehensive view of the Earth. But SWOT will give us that comprehensive view because it will be a satellite orbiting the whole globe. And then with respect to ocean, SWOT will give us a better understanding of how the ocean's role in climate change. The oceans absorb a lot of heat and carbon, and this will help us better understand that. And so it is targeted to launch in November.
Thank you. So this wraps our Q&A session. I want to thank you all for joining us today. Thank you for all of your questions. I would also like to thank each of our speakers. It wraps our briefing. Tonight at 8 p.m., you can listen in to our pre-launch news conference at nasa.gov/live. Please also join us tomorrow for live launch coverage scheduled to begin at 8:15 p.m. Eastern. That will also be on nasa.gov/live. For more information about NASA's SpaceX resupply missions, please visit nasa.gov/SpaceX. To learn more about Emit, visit earth.jpl.nasa.gov/Emit. And finally, for more information about NASA's Earth science missions and our climate research, please visit nasa.gov/Earth. Thank you.